So in section 6.3, we're going to talk about similar polygons and what it means to be similar. And we're going to talk about similarity, especially in triangles, for the whole entire rest of this chapter. In chapter 6, it's kind of like the big idea of chapter 6. We have just been working on proportions because proportions are a big part of similarity. So on your formula handout that I have made for you, similar polygons have congruent corresponding sides and angles and proportional corresponding sides. So all angles are congruent. This is not exactly this is not exactly what it says on your sheet. So this is an extra one, so I need to put that one on your sheet too. I'm going to give y'all an addendum to your handout. Extra. That's what addendum is. It's like an extra thing attached. Oh, okay. Anyway, so anytime they tell you something is similar, that means it has congruent angles and sides are proportional. So they will have the same shape, but they will not necessarily be the same size. Remember, if they were congruent, they had the same shape and size. Similar means they have the same shape, but not the same size. Okay, so that's the difference in similar and congruent. Similar, same shape, not the same size. Congruent means same shape and same size. So the angles will be congruent. So on these two quadrilaterals, because they have four sides, angle E is congruent to angle A, B is congruent to F, C is congruent to D, D is congruent to H. And just like when we name congruent parts of triangles and things like that, when you see the similarity statement, that little squiggle line means similar. One squiggle line means similar. Remember that a squiggle line plus an equal sign is congruent. So one little squiggle means similar. They are written in order of what they're congruent with their corresponding angles. So A is congruent to E, B to F, C to G, and D to H. All right? So angle measures are congruent. Sides, corresponding sides or segments, are proportional. So you can use the name AD is proportional to EH, AB to EF, CD to GH, and what I skip, BD to FH. Okay, so all their sides are proportional to what they correspond with. All right. Draw those triangles, please. And write down that similarity statement that they gave you. Triangle RST is similar to X, Y, Z. And I'm going to write that up there on our board somewhere. S, D, C. All right, the first one is really easy. They want us to list all pairs of congruent angles. You don't even need the pictures to do that. Okay? If you have the similarity statement, and we do when it says triangle RST is similar to triangle XYZ, then we can just list them with their corresponding angle. Okay? So angle R is congruent to which angle? Angle X. Angle S is congruent to which angle? Angle Y. And angle T is congruent to which angle? Angle Z. Does that make sense to everybody? So you can use your similarity statement right there to help you decide which ones correspond to each other. And for a similar triangle, all angles are equal. They're congruent. The measures are equal. Then it says check the ratios of corresponding sides. So what we're going to do is we're going to use our similarity statement on number one, beside number one up there that I have a box around. And we're going to list the pairs that are supposed to be corresponding sides. And then we're going to plug their numbers in and see if they actually are proportional. Congruent ratios. So side RS is supposed to correspond with what side in the second triangle? XY. I'm just going to write these down and skip a space. ST is supposed to be corresponding to which side in the second triangle? YZ. And then RT is supposed to be corresponding to which one? XZ. So when it says to check the ratios, I listed all my pairs of corresponding. Every ratio should simplify to the same number. Okay? So what is the length of RS? 20 over what's the length of XY? 12. And let's reduce that fraction. Divide them both by 4, I believe. And what do we get? 5 over 3. So all of the other ratios should also reduce to 5 over 3. So that's what we're verifying, that they all have a 5 to 3 ratio. Why do you think it's an improper fraction?
Because the bigger triangle is first.
Yes, we did the bigger triangle first. That's right. So if your bigger triangle comes first, then it's going to be an improper ratio. If your smaller triangle comes first, it's going to be a regular ratio. All right, so what's the length of ST? 30 over what's YZ? 18. And those are both divisible by 6. And what does that reduce to? 5 over 3. So far, so good. We have equal ratios. And then we check the last set. What is the length of RT? 25. And what's the length of XZ? 15. And what does that reduce to? Yeah, divide them both by 5, you get 5 over 3. So that's what it means when it says check the ratios of corresponding sides. You use your name, your similarity statement to tell me what sides are supposed to be proportional, and then you plug in the numbers and make sure they all equal the same ratio. Okay. The next thing says write a statement of proportionality for the sides. That just means you take these things and set them all equal to each other. So that just means you say R over S over XY equals ST over YZ and also equals RT over XZ. So that's what a statement of proportionality is. If they all equaled 5/3, then they all equal each other. All right, I'm going to skip the next example if that's okay with you. We're going to use this to solve some problems now. So take a moment, please, and write the similarity statement and draw the picture for me. Now, these are kind of simple to start with because if you notice the two triangles, while it tells me they're similar, and while I have them different sizes because that's what similarity means, they're still oriented the same direction, right? They look alike because they're in the same position. One is not flipped and rotated, They're all like this side on the bottom, the hypotenuse. If it looks like a hypotenuse, it's not really a right triangle. We can't assume that. But the longest side appears to be right here. For both of them in the same position. So they're in the same position. That's not always going to be the case for similar triangles. Sometimes they'll have one rotated around sideways or upside down or whatever. But we're going to find x. So x is segment EF, is it not? Right?
Yes.
EF is proportional to what side?
NP.
NP. So that ratio is x over 20. And x is in the little triangle, is it not? I like to label when I have a little triangle and a big triangle. So that way I can keep all my littles on my numerator together and all my bigs on my denominator together. Because you don't want to talk, you want to make sure you're talking about the same triangle in each the numerator and the denominator. Okay? So, I know all the other sides, don't I? So all you have to do is pick a pair of proportional sides, one from the little triangle and one from the big triangle that you know both of them. So somebody give me a pair that they want to use.
DE.
Okay. So we know that DE should be proportional to MN, right? So the little one's number was what? 9, and the big triangle's number was 12. Y'all see that? You have to use two sides that are proportional to each other, and you can check them in the name. DE corresponds to MN. Okay? So now we have a little proportion, and we can solve it for x. So cross multiply. X times 12 is, and 20 times 9 is, 20 times 9 is 180. And then I divide both sides by 12, and what do I get? 15. Did I get units? Nope. And all it said was to find x. So I'm done. So any questions about that? So you use the ratio where the variable is, and then you find a ratio of two corresponding sides where you know both of their measures. All right? I'm not going to make you draw this picture, but please set up the proportion with me, and it might help you to write the statement of similarity. We're finding x. What is the segment that x is on? HJ. Which segment in the little triangle does HJ correspond with? BC. And if you can't tell by your picture, use your similarity statement, okay? HJ corresponds to BC. So if I'm doing little over big again, it don't matter. You might want to use big over little because that's where X was. It don't matter as long as you're consistent on all the little stuff stays on the same row and all the big stuff stays on the same row. Does that make sense? So if I do little over big, I would say 16 over X. Does that make sense? Now somebody give me a pair of corresponding sides where I know both of their measures. AC and GJ, and double check. AC does correspond with GJ. So which one is the length from the small triangle? And what's the length from the big triangle? And then you cross multiply. X times 12 is. X times 12 is. And 16 times 18 is. 288. And then you divide by 12 and X equals what? 24. So you don't have to pick. You could have used which other sides? Yeah, you could have used 8 and 12 as your other ratio. Does that make sense? Because you knew all of those measures. I want you guys to try that. You don't have to draw it. You can just set up your proportion. Y'all try it. Your proportion can look different from somebody else's. It just depends on which corresponding side you use for the other side of the proportion. But you still should get the same thing for x. All right. So, which side has x?
BC.
BC. Does the one on the left look bigger than the one on the right?
Yes.
So I'm going to do big over little. I like going left to right. It doesn't matter. Okay? As long as you have the right ones in the right place, which whatever your proportion looks like. Y'all's might look different than mine, but it's okay. So BC is x, and it's in the big quadrilateral. What is the measure of the side in the little quadrilateral that it corresponds with? 4. So for one of your ratios, do y'all have an x over 4 or a 4 over x? Okay. So 4 and x correspond with each other. Somebody tell me a pair of corresponding sides in that we know both of their measures.
DC and 16.
Okay. So 16 for DC in the big quadrilateral and 8 for TS in the small quadrilateral. Y'all agree that they correspond with each other? And we know both their measures. So if I'm doing big over little, I'm going to do 16 over 8. If you're doing little over big, you would use 8 over 16 if you use those sides. You could have used a multitude of other sides. Right? Well, not really a multitude, like 4 pairs. 3 pair, actually. So if I use this one, I have 8 times x is 8x equals 4 times 16 is 64. And x equals 8. Raise your hand if you got x equals 8. Did anybody not get x equals 8? Okay, so we all got the same thing. We're going to stop right here, which is halfway through section 6.3. Thank you for watching me on YouTube.